Good morning. So to recapitulate a little bit from last time, what we showed was, with great effort actually, we went through each of the axioms of ZF and showed they held in L. So our picture of the universe at the moment then is we have our universe of all sets V here, and we've carved out within V this possible subclass, this kind of cone that sits inside the other cone. And this is L. So these are the constructible sets. And we have the ordinals going up the center of the cone here. And we showed so for each axiom, sigma of ZF, that sigma held relativized to L. So in short, we'll write that like that. All of the axioms of ZF hold when relativized one by one to L. So we've got an inner model of the universe. And it's a model of the theory ZF. So the same axioms hold in L as hold in V. Right? So a number of questions, I said, immediately arise. Does L equal V? Right? It's possible that the construction of L, where we took this definable power set operation at each stage, actually recovers all of the sets in V. The V construction takes the whole power set in one go. But the L process is a little slower. We saw that when you take the definable power set, the size at each individual level doesn't grow. It's not a larger infinite cardinality than the level before, which is the opposite of what happens with V. So it's possible with L that it grows slowly, but actually, in the end, it defines all the sets that are in V. That's a possibility. So this question we'll come back to later. But what we're going to do today is see, one of the reasons that Gödel defined L was to show that it was consistent with the axioms of ZF, that the axiom of choice was true. And that's what we'll do today. We'll show that the axiom of choice holds in L. And what we'll do actually is, let me draw L again, slightly wider. So here's L without V around it. What we're going to do is show, in fact, that there is a well-ordering of all of L. So we'll show that there's a formula, so giving us a term, if you like. And this will be a well-ordering of all of L. So it's not that the well-ordering principle, not only that the well-ordering principle holds that any set can be well-ordered, actually, it's much finer than that. We've got a way of well-ordering the whole universe in one long well-ordering of length ON, right, of length the ordinals. So in particular, we can use that well-ordering to well-order any one particular set that we might be interested in. And that well-ordering principle is equivalent to axiom of choice here. So the task today is to define, well, this formula and therefore this well-order here. And in brief, the idea is, because the definability operator has such a neat definition, we can use the definability operator to give an ordering on our definitions. So this here is L alpha. We use the def operator to give a well order to our definitions over L alpha to extend a well order here less than sub alpha of L alpha to a well order of L alpha plus 1. So the idea will be, let's suppose I've already got a well order of this much. I look at what goes into the next level, right? Everything that goes into the next level is given by the def operator. So there are only countably many definitions, right? Countably many formulae of the language. So I can just list those, right? So there's an omega sequence of those formulae. I've already got, inductively, if you like, a well order of L alpha. So I can use that to well order the finite sequence of parameters. In other words, the valuations that I could use on those formulae in order to define something in the next level, L alpha plus 1. So I combine the well order of the formulae with the well order of the possible valuations, which comes from the well order of L alpha, to just list the definitions that go into the next level here. And we just keep doing this. Right? At limit levels, we'll just extend the ordering that we're building up by taking unions. So everything end extends everything else. And then at the end, we take a union of the whole lot to get our well ordering of all of L. So that's the tactic that's coming up, right? And which we'll do today. So let me arrange this here. So I see there's a question. Somebody thinks I may have made an error in the pre-recorded lecture. I'll deal with that at the end, if that's the case. So we're looking at section 4.2, the axiom of choice. So we first assume in general so the structures we're interested in are really only sets. So just take a set X with epsilon, with its single relation on. So we'll assume we've got a well order of X. So, and I'll just write it as this. So we use this to well order the valuations into the set X. So recall what QX is. This is the set of H's, set of functions that go from omega into X, which are constant from some point onwards. So though officially having an infinite domain, they're only interesting up to n0, for some n0 or other. Yeah. So this is what Qx is. So this ordinal, this integer, the least integer n0 for which this is true, we'll call the length of H. So for f in Qx, we'll define the length of f, okay, is the least n0 such that for all m greater than or equal to n0, hm is hm0. So that's the length of the interesting bit, if you like, of f here. So we're going to define here a well order of Q sub x using the well order we've already got of x. I'm going to say that f comes before g if and only if the length of f is less than the length of g. Right, so shorter ones come before longer ones. Or, let's say they've got the same length, but we look for the first place where they differ, right? If these are different valuations. So we look for the first place where they differ, and we see which one delivers at that first place a smaller element in the well order of x. So we're going to say there is a k less than or equal to the length of f, right, which is the same as the length of g. And what we'll have is that f of k comes before, in the ordering on x, g of k here.
So what one should check is that this is a well order. Well, you first minimize on the lengths. Given a whole bunch of elements here, take a non-empty set of element valuations. You need to show that there is a least element in this well ordering. Well, given that on that set of valuations, look for those that are of least length. So we minimize those on length. And then when you look at all of those which have the minimal length, if that length is whatever it is, right? Then look and see, right? For all of those Ks, yes, look at those. Look at all of those of that same length. Then find the least K where things differ from each other, and check and see which one here then delivers the least element of X for you. Right? So that's what will give you the fact that it's a well order. One should check that it's also a total order as well. Right? Well, pick any two elements, either this happens, right, or they're equal, and because they're different, something has to happen, right? Either it's this way around or it's the other way around for some K. So it's also easy to check that it's a total order as well. Okay, so we now suppose we have a listing phi 0, phi 1, phi n. And this consists of all of the formulae that one could put into the def function, right? So we want a list of those formulae which have at least v0 as a free variable. As a free variable. So these are suitable to put into the def. So that they're suitable for putting into the def function. So putting into our definitions that make up the def operator. So they're only countably many formulae, so we can make a list of those. In fact, one could make a recursive or computable list there. Okay. So next stage. So we'll define here definition 4.9. So we're going to define by recursion the ordering less than sub alpha, and this is going to well order L alpha here. So L0 is the empty set. So this ordering is also the empty set. So assume less than alpha defined, and we'll define the next stage. So as I said on the board, here's L alpha. I'm assuming I've got this well order here of all of L alpha. And I'm putting on this new stuff on top. So there are some new objects up here in the next layer of the cake, and I have to just order them. I want to stick these on, the new things, on after the old things. So I want this ordering here, we'll say end extends the previous ordering. So the new gadgets should come after the old gadgets. I mean, there's a little thing that one can say about this here. I mean, when we look at the def function and we look and see what's definable over L alpha, we saw, and indeed it was an exercise, to show that every finite subset of L alpha was definable over L alpha. So actually, when we look at the list of definitions, some of the definitions will give us new objects, new subsets of L alpha, to put into L alpha plus 1. And some of the definitions will just be repeating what we've already got. So we don't want to reorder the things that we've already got. We only want our new order to extend the old order on the new objects. We don't want to rearrange the old order. So this is what we mean by it being an end extension. So this is going to be an extension of L alpha as a set of ordered pairs, and will be an end extension. And I'll define that more precisely when we actually come, well, you'll see this when we come to actually define what the ordering is next. Okay, all right, so that's good. I see that chat questions answered. Okay, so we're still continuing definition 4.9 here. So we're going to say X comes before Y, right, for X and Y in L alpha plus 1. This is the task we're doing. We're defining this ordering here. So if and only if, so we're going to define it in this way. Well, first of all, X is something old and Y is something new. So maybe X occurs here and Y is up here. So the old stuff comes before the new stuff. So if and only if X is in L alpha and Y is not in L alpha, right? So Y is up at the top, it's something new. Right? Or they're both down here, and they're already ordered according to less than sub alpha. So if they're both in the bottom part, we stick with the old ordering. And then now is the most difficult part here, is when they're both new things up at the top. So this will cover a line in a bit. So X and Y are both in, well, they're in the top, right? So they're up here. We now have to decide or arbitrate which one we're going to put down first here. So now we look at the definitions that we've got for X and Y, and we'll decide which one comes first in the ordering on the basis of the least definition in some sense. So they're both at the top, and we're going to say there's a natural number n, and there's a valuation here. So that X is the interpretation of, or the definition given to us by the formula phi n, matching over here, right, using this valuation. Right, so again, just to recall down here what this means X is the set of Z in L alpha such that L alpha epsilon, where we put in here, here's the valuation, F, but what that does is 0 is it returns Z here. So this is X being this is this iota applied to L alpha, the formula phi n, and the valuation. Okay, so X being something new, it's got a definition like this. Def is the collection of these. And now we're going to say there is this definition of X that comes before all the definitions for Y. So we'll now say for all M in omega and for all G, which are valuations, if Y is defined over L alpha using phi M and valuation G, then either phi n is an earlier formula on our list than phi m, or they may be the very same formula, but the valuations are different. And we then use the order on the valuations that we had before. This one. N equals M here, and F comes before G. Here. So this bracket goes with this one, this bracket goes with this one, and that's it. And one more here. So a huge stack of brackets going on there. Okay, I don't know if there are any questions about that ordering. I mean, you need to look at it and puzzle it perhaps a little bit more there. But this is, you can see perhaps what I'm talking about, this new ordering being an end extension of the old ordering, according to this picture here. because we put the old ones before the new ones. We respect the old ordering, right? It extends the old ordering as a set of ordered pairs here, right? And then we decide what to do with the new things. So this is how we define the well ordering of L alpha plus 1. Right? For a limit case, if lambda is a limit, then less than sub lambda is just the union of the previous orderings. Which is fine. All this is meaning is I take all of these and I just union them up. As they extend each other on the way, this is not a problem here. And now our ordering of L is the union of all of these. Here. So now the picture is, I've just done this all the way up through the whole universe. Right? So of course here, this is a proper class. It's well ordering. Every element of L is in the field of this ordering here. Each of these is ordering the set L alpha. This is ordering the proper class of L here. So some properties here of this well order. So alpha to here this is a definite function. Again, of course, one would have to look back at what did definite mean. We've defined this by recursion. Right? So we're using definite recursion, but only about definitely definable gadgets. Right? The function that goes from beta to L beta is definite, right? We've said. The function that gives me a set of valuations over a structure Z, right? That is definite here. And likewise, an interpretation. This is all given by a definite expression. So I just claim here that this is a definite function. So less than beta here is a well ordering. And end extends. Less than sub alpha for any alpha less than beta. Yeah. Third property here is if I've got an infinite cardinal kappa here, then the ordering of L kappa has order type kappa. So that's the length of the ordering on cardinal L kappas. And hence the axiom of choice holds in L. Okay. So what have I said there in the way of proof? Well, I've just said that I've just claimed it. This is defined by definite recursion. Right. And I haven't said much more than that. So we only use definite terms when we wrote out the recursion, defining the next level from the previous level. And at limits, we took unions, which is a definite process. Sorry, lambda. So this is for limits lambda. So taking a big union of a set of well orders this is a definite process. So I'm just saying a little there to hope that it may look plausible or indeed convincing, right, that this is a definite recursion. And I'd say that two said that the ordering is a well ordering and extends. This is an induction on alpha, right? I mean, if we're assuming that less than sub alpha is a well order already, what we're doing is putting these new things on here, and we're using the well order on the valuations to order these definitions, right, using our well-ordered list of formulae. So altogether, we've got a well-ordered list of definitions going up there. And I've remarked already on the fact that we're end extending here. So I don't think there's much that one needs to do here. The length of the ordering of L kappa when kappa is a cardinal, I've left that as an exercise. So I mean, the hint here is, I know that kappa is contained in L kappa. So there are certainly kappa many things here to go into the well order. So the order type here of this has to be at least kappa. It can't be some smaller ordinal order type because the cardinality is too big, right? If there were a smaller order type, that would give us a map from kappa into something smaller. It can't happen because kappa is a cardinal. Right? So we want to show that this is exactly kappa. Well, just show that there can't be anything beyond kappa, right? So show for a contradiction. If this order type here was strictly bigger than kappa, there'd have to be something that was the kappath element in this well ordering. There'd be some x in L kappa So that if I looked at this ordering here, and I restricted it to the predecessors of X, and I'll write that like that. So the initial segment of the well order determined by X. So that X, I mean, if this order type is bigger than kappa, there's going to be some X, which is the kappath element. So there's some X, a member of L kappa, such that this here has order type kappa. So i.e. X is the kappath element. And that will be a contradiction. Because actually X is then in some L alpha, where alpha is less than kappa. But these L alphas have cardinality less than L kappa. So this is a contradiction. Right? So you can then show why, well, say why that is a contradiction. Right? And again, it's because X would then be in some L alpha, which is too small to have kappa many predecessors of this X. So you're using a fact about the size of the smaller L alphas, and you're using that the orderings are end extensions. Okay. Any questions there about that? Okay, so think about how this proof goes, right? It's a popular, if you look back through old exam papers, it's a popular question to ask about sketching this proof here, or proof of the GCH to come, or the axiom of constructibility. So you need to know how these arguments work. Right? So to sum up, we've shown that this here well orders L. So we have some formula which defines this. So this is the formula defining the recursion, kind of implicit in this scheme here. So this is the formula implicit in the recursion scheme, or the definite recursion scheme, defining the function alpha to this ordering here. So that, I mean, if I were to look at this here, this is the collection of x, y. such that phi xy holds here. This is the well order of L. So the formula is true only of pairs of constructible sets. And if it's true of this pair of constructible sets, it's because X comes before Y in that ordering. So there's one formula that defines this. So we say that L has a global well order. Global because it orders the whole universe of L. Right, so it goes through everything. So that's a very strong form of the axiom of choice. As I said, the axiom of choice just says there's a choice function for every collection of non-empty sets, or equivalent to saying every set can be well ordered. This is stronger than asserting AC or WP, because these say just things about sets, right? The global well order says something about this proper class, L. The fact that this is a global well order says something about a proper class. Namely L. In general, the axiom of choice does not imply the global well ordering property. That we have a global well order of V. So I would say ZFC here does not prove there's a global well order. But of course, if there is a global well order, you can well order everything. Well, you can certainly well order every set. So obviously, the implication goes in the other direction. Does imply the well ordering principle. A global, so I'm just trying to abbreviate here. Global well order implies the well ordering principle here. And it's because of the very kind of uniform way that we can define L that we can impose this global well ordering on it. So it's only because we have this nice uniform way of defining the L alpha levels that we can impose this. We can impose this global well order. Or we can identify or define this global well order. Okay. So we'll see either in the next lecture or the one after how we can show that we've got a relative consistency result. But basically, the intuition is, once you've defined, basically the intuition is that a principle or a concept is consistent if you can find a structure in which it's true. 2 + 2 = 5, right? I can never show that is true in a structure, because 2 + 2 will always be 4 in a structure. So if I've got a principle such as the axiom of choice or this global world ordering, if it's true in a structure, then it's going to be consistent. And what we've done is show that AC, or the world ordering principle, is true in L. So it's consistent inside the universe L. So it's basically what we've managed to, or what Gödel managed to do. Maybe that L is not V, but that doesn't matter if you're only interested in a consistency proof. We've shown that it is consistent with the other axioms of ZF. We'll say that more formally, right, next time. Okay, if there are any questions, please let me know. I just want to add, there was somebody sent through to me that I may have made a mistake in the pre-recorded lecture when I wrote out the axiom of foundation. As I said, the intersection was non-empty. I will look and check that. Maybe I should have said that it was empty or something. I don't know exactly what point that occurred. But I'll let you know if there's anything to be changed there. Okay, are there any questions? Otherwise, we'll say goodbye. Okay, fine. Good. I'll see you tomorrow then.